Welcome. I'm Gwen Bell, Director of the Computer Museum, and generally when we have these, I've had the pleasure of announcing a number of openings. I think the museum has opened at least 5 times. Well, this celebrates closing. This is really our final lecture at this place while we're open here. There will be, like the Boston Pops, there will be an encore. That is, there will be another lecture by Robert Langridge on December 10th, but the museum will be officially closed. So we'll have a number of closings as well. And I hope to see you back at the encore and then at the Children's Museum downtown sometime next year. Bill Strecker is going to introduce Bo Evans. Bill generally is known as the museum as the husband of the store lady, but he's been responsible for a lot more things, including the architecture of the VAX, and so we thought it would be appropriate for Bill to introduce Mr. Evans.
Good evening. It's my pleasure this evening to introduce the speaker. Bob Evans is an IBM Vice President, Engineering, Programming, and Technology. Mr. Evans joined IBM in 1951 as a junior engineer in Poughkeepsie, New York, where he took part in the development of IBM's first large-scale computers. After various assignments in computer development, he was promoted in 1962 to Vice President of Development for the Data Systems Division. In January 1965, he was named President of the Federal Systems Division, which develops advanced products in the national interest. In 1969, Mr. Evans was promoted to President of the Systems Development Division, responsible for the definition, architecture, and systems management of IBM's principal computer product lines, and systems management and was elected IBM Vice President in June 1972. He was appointed President of the System Communication Division in May 1975, responsible for the designing, developing, and manufacturing of terminal and communications-related products. He was named to his present post in April 1977, responsible for coordinating the effectiveness of IBM's worldwide engineering, programming, and technology activities. In addition, since 1974, Mr. Evans has been a member of the Partners and Executive Committee of the Satellite Business Systems, a partnership involving Aetna, ComSat General, and IBM. He is responsible for coordinating IBM's involvement in this communications satellite-based company. Mr. Evans received a BS degree in electrical engineering from Iowa State University in 1949 and has done graduate work at Syracuse University. In June 1971, he was awarded Iowa State's Professional Achievement Citation in Engineering. He is a fellow of the Institute of Electrical and Electronics Engineers, a member of the National Academy of Engineering. He served on the Defense Science Board, is a member of the Board of Trustees of Rensselaer Polytechnic Institute, a member of the MIT Visiting Committee for the Department of Electrical Engineering and Computer Science, a public member of the Charles Stark Draper Laboratory, a member of the Board of Trustees of the New York Library, and a consultant to the Science and Technology Advisory Group of the Executive Yuan Republic of China. An impressive list of achievements. This evening, Mr. Evans is going to be speaking on IBM System 360. The System 360 was announced in 1964 and at the time was a revolution in systems architecture, technology, and programming. At the time, the IBM 360 was an enormous risk for IBM because it obsoleted all of IBM's existing computer products. The IBM 360 was expected to endure for no more than 8 years, but today, some 20 years later, the architecture is still the foundation of IBM's system product line and shows no signs of abating. This evening, Mr. Evans will describe the events, counterforces, actions, and reasons that permitted IBM's ranks to close and produce the System 360. I'd now like to present Bob Evans.
Thank you, Bill. Ladies and gentlemen, it's good to be here, although Bill missed one of the things in my list of things. I'm also a notary public. Mrs. Bell and Dr. Bell and ladies and gentlemen. I'm delighted to be here and glad to be asked, and I hope that what I have to say is worth your time. I'm especially honored to be here in the presence of some of the truly greats that have founded the information industry that we know today. Dr. Selfridge has been one of my intellectual heroes for all these years. In the room is Professor Maurice Wilkes, one of the founders of the industry, who did the basic work working with Dr. von Neumann at the Institute of Advanced Studies, and then back to his native England to build a machine actually ahead of the work at the Institute of Advanced Study. And of course, Gordon Bell. Everybody has their viewpoint of who's really good. My view is that Gordon Bell is one of the three outstanding proven architects, computer architects living in the world today. My view is Gene Amdahl, and the other is IBM's own Dr. John Koch, still working away happily in our research organization, but I'm honored to be in your presence. I want to describe System 360. I have to tell you that I've been with IBM 32 years, so I'm a company man, and I will tell it as accurately as I can recall from the times that were wonderful times and stressful times for the company. I'm uncertain about the value of 360 to you all. There are certainly some management lessons in its gestation and what's happened since. I'll try and enumerate those as we go. I will say that System 360 and the direct descendants have accounted for more than $100 billion worth of revenue and a pile of profit for my company, and has indeed, as Bill said, been the foundation of our basic business for years longer than we thought. I'm going to spend just a moment on the background to set the stage about IBM and how it started, although I'll not spend long on that and hope not to bore you. Big pile of view graphs, but have heart, they go very fast. IBM was formed in 1911. At that time it was called the Computing, Tabulating, Recording Company, and it was formed from an amalgamation of three tiny companies that worked on things like meat slicers and scales and nurse call systems and whatnot. One tiny corner of the company was the Tabulating Machine Company that had been formed from the intellect of Herman Hollerith, the inventor of the punch card. And this struggling little company in those days, recording a few tens of thousands of dollars of revenue, grew slowly. The 1930s, though, in the early 1930s, it had grown substantially. Amazingly, that it had shed itself of most of the prior things, the nurse call systems, the scoreboards, and the meat slicers, and it had concentrated on the Hollerith concept. And by the 1930s, it was an electric accounting machine company. There were several reasons that accounted for the success. First, the strength of the concept itself. Secondly, the old fellow that ran the company, a young man at the time, Thomas Watson Jr., that had grown a National Cash Register company, and the U.S. Social Security Act of 1931, which created enormous demand for the kinds of machines that this company built. The Computing and Tabulating Recording Company title was renamed to IBM in 1924. But let me just give you a perspective on the sales of this little company in the decade of the 1930s. 1930, IBM was $19 million a year, and it grew reasonably handsomely to 1939 to whopping $38 million a year. More important, the measure of the effectiveness of the company might be the profits. This is net earnings after tax. One would say these days that those profits are obscene. That 1930, 36.8% net earnings after tax. Of course, the tax structure, corporate tax structure in those days was substantially different. Even in 1939, tax The margin was 23.7%. So it was a healthy little company bubbling along, producing electric accounting machines for a growing demand. By 1949, IBM had grown to be a $200 million a year business, and it was almost all electric accounting machines. And while people from Sperry Corporation would carp at me, the view then was that, at least in IBM's viewpoint, as they were the product leader in electric accounting machines. I've already said it's a very profitable institution. Investors loved IBM. If you bought a buck's worth of stock in those days, you wouldn't have to work now. Very strong user loyalty to IBM, and most important, there was a very abundant opportunity for new electric accounting machines. I thought it curious as I reflect on IBM that years before it had turned the corner from a successful set of businesses in nurse call systems, meat slicers, and all that kind of stuff that it knew very well, to move into the untried area of electric accounting machines. And in a moment, we'll be talking about another corner the company turned at the very time that it was best in electric accounting machines, and there was substantial opportunity. To breeze on, though, let's look at old IBM for the decade of the 40s. This is changing scale now. It's a $200 million scale, and these are the numbers you saw before in terms of sales and profit. Now let's look at 1940 through 1949. What you see is, of course, the bulge that came during the war years as the company, like all industries, turned to the national effort. And then you see some downturn as the companies recaught their breath to get back in their basic directions of business. Equally interesting is the profit production of this company, the decade of the 40s. At 20% earnings in 1940, consistent with what you saw in 1939. Profit grew to a nice $33 million, or 18% net earnings after tax in 1949. You see the effect of the war years, where some commercial business continued, but the bulk of the business was very low profit national interest work. As a side point, that from the national interest work that was done during the war years, where IBM produced fire control systems and navigation and bombing systems, among other things, the military products division grew and has endured. It's been renamed some years ago the Federal Systems Division, and still works in the national interest, although the revenue of the Federal Systems Division is less than 2% of IBM's overall sales, and the profits are commensurate with aerospace industry profits, and so not much of a factor. Strange thing happened that led IBM to turn another radical corner. One often wonders how these things happen, and in reflection, this was most unusual. For here was IBM bubbling along with electric accounting machines, doing very well. And the Korean War broke out. Old Mr. Watson was a super patriot in a splurge of patriotism. Shortly after the war broke out, he sent a telegram to President Truman offering the IBM resources, whatever, to the national effort. The bureaucrats in those days were sophisticated enough that it was a different time. They didn't know quite what to do with Mr. Watson's offer. And the consequence of this telegram that rattled around the hierarchy in Washington was that a couple of IBM people would look at the national laboratories around the United States to determine if there were anything that IBM might do. One was an engineer named Ralph Palmer, now retired, living in Connecticut. My viewpoint, another of the geniuses that IBM was fortunate to attract, who really laid the foundation of IBM's development community that still exists today. The other was a super salesman named Cuthbert Hurd. In the room is my friend John Griffith, and he and I, for 30 years plus, have wrestled with and wondered about Doc Hurd, legendary salesman. Left the company several years ago and has been in and out of computer operations since, lives in California, and works in several related areas. But Hurd, a master salesman, Palmer, a master engineer, under the aegis of the Watson telegram to the president, toured the national laboratories. They looked at Sandia and Los Alamos, and they looked at aerospace companies where things were going on that IBM might contribute to. And when they came back, their conclusion to old Mr. Watson was that the best thing that IBM could do was build a high-speed computer, like the high-speed computer that Dr. von Neumann and Professor Wilkes and their colleagues were building at the Institute of Advanced Study. They thought that there were such a demand for computation in these national interest areas that we could do so. We should do so. The government wasn't all that interested in it, and so Mr. Watson, anxious to keep his pledge to the government, decided to fund that effort. And so in 1950, late 1950, the project got underway. The viewpoint then by the dominantly EAM company was that this is a great intrusion on the mainstream of things that were going on. Estimates of the kind of markets for these kind of machines were 10 or so, and the costs were astronomical. The viewpoint, this was indeed a national sacrifice, and we'd get on with it and get it over with and get back to our basic business as swiftly as possible. Now, turned out that, and John Griffith worked on that machine, the fellow sitting here in the room. Where are you, John? There you are, sitting by Professor Selfridge. Called it the Defense Calculator, the 701 electronic data processing machine. The first one was installed in IBM's world headquarters in New York City in December 1952. I was lucky enough to be one of the engineers that went down to try to get that sucker going, and we had a lot of trouble. 19 were built in the years 52, 53, and 54. The rental of this thing was a staggering $20,000 a month at a time when IBM machines, if they rented for $300 a month, was a lot of money. So it was totally in high space and didn't have much promise. But what happened was, fortunately for IBM, is old Mr. Watson Jr., old Mr. Watson was aging. His son was growing rapidly in the ranks, Tom Watson Jr. Tom had risen quite quickly to become president of the company, and he'd earned it, in my opinion. And he saw the potential of electronics through all the clouds and all the obfuscation. You can imagine the senior management of the company, they knew the AM business, they loved it, they had all these things they needed to do to expand the business, immediate customer requirements. I thought it was very unusual for a company in that position, of those profits, that kind of growth, to turn the corner to electronics. But Tom Watson led the business to that. Moving swiftly ahead then, from the World War II, had come the vacuum tube technology. In the period 1952 through 1956, a lot of computers came out of IBM. In the business arena, machines characterized by being alphanumeric, handling both alphabet and numbers. Serial by character, for those voluminous strings of variable character lengths or word lengths, and with a lot of peripherals, usually tape devices, that characterized those machines. And as a continuation of the applications found by the old defense calculator, the 701, a better version was produced called the 704. Gene Amdahl had come to IBM from the University of Wisconsin, where as a doctor's thesis he had built a machine called the WISC. Came into IBM, he, John Griffith, and a handful of people worked on the architecture of what became the 704, floating point, indexing, a lot of bright strides forward, and later on, core memories, replacing the old Williams tube memories, 709 was built. The 650 business machine sold a little more than 1,000. Forecasts when the thing was announced were 50, and so bonanza hit, and IBM was on its way into electronics. The 305 was a product of Ralph Palmer, that engineering genius's mind. He wanted to see business data immediately accessible by the processors, and he envisioned a disk device. Set up a laboratory, IBM's third, in San Jose, California, to go out and develop disk devices. And the 305 was the first disk system that IBM produced. Its forecast was something like 4,000 or 5,000, if I remember, maybe a little less. it only sold about 3,000 because it wasn't fast enough, had a lot of programming problems. We all know that story. And it went through some troubled times, superseded later by other machines. The 702 and the 705 sold a couple hundred machines. Again, these rentals of $30,000 a month took the place of a lot of sorters and collators and gang punches that were then the mainstream of IBM's business. The 704 and 709 sold 250, 300 machines, big rental, big ticket items, and they too brought in a lot of new revenues to IBM in this exciting new era. Important thing to note, though, is that IBM had bolted off scientific direction in one regard, the business or commercial applications in another regard, and families of machines, albeit different families, were getting to grow in those directions. How'd the business do? Let's change the scale again now. We'll go to 2 billion, and here are the numbers that you saw through the decade of the 30s and the 40s on the $2 billion scale. Here are the sales consequences of that shift of gears to electronics for the decade of the 50s. IBM grew swiftly, crossing $1 billion in 1957, and in 2 years after that, it reached $1.6 billion, fueled by the movement into electronics. Incidentally, this is before Gordon and DEC and those marvelous companies. People that were working in computers those days, some were ahead of IBM, and I would have to say now in a simple statement from an IBM viewpoint that the way IBM was able to succeed so well was fundamentally a marvelous sales force and a marvelous service force. I think those things, not especially excellence of equipment, were the keys to IBM's able to move out as they did from a tiny company to a very significant company. Bottom line on margin was that heavy investments were going into electronics, net earnings dropped, and new taxes were coming. Margin dropped to after tax to 10.9%, healthy by any measure in those times. And so the company was doing very well. If I then take us into the transistor age, IBM announced its first transistorized machine in 1957, delivered it in 1958. Through the period 1959 and 1960, brought out a whole slew of transistorized machines, some new architectures, and I'll describe them, some old architectures built on the vacuum tube predecessors. For example, the 7080, and here I've put those together back to back as opposed to what you've seen before. Performance for the business class is upward, performance for the scientific class, as you can see, is downward, and price generally goes left to right. 7080 transistorized machine was a transistorized version of the old 702, 705 commercial machines. It was brought out actually because the 7070, a new architecture, had not done as well as had been expected. Customers that had 702s and 705s weren't converting their programs to the radically different architecture of the 7070. Less than 100 of those machines were produced, yet it was a business success. The 7070 was IBM's great hope for a new age of architecture with transistors. RCA had come out with the vacuum tube Bismack series that a few gray hairs in the room might recall, and then they had moved to their 500 series, as I recall. The 501 they announced the machines, had marvelous performance, great price. They were transistorized machines, and IBM was racing to compete with the 501 before it lost the heart line of what it considered its business. And incidentally, the business side, commercial side, was viewed as being 80 or 85% of the demand in those days. The scientific side was viewed as being 15 to 20% of the demand in those days. 7070 was the hoped-for new era of machine that would retain IBM's position, and we'd grow from that base. The genius Ralph Palmer had done something that he had characteristically done. He had a competition to see who was going to design the 7070. The Poughkeepsie Laboratory, the big machine laboratory, had a design that was an attractive machine, and they vied for the honor to build IBM's new transistorized business entry, the plum of the development community. The Endicott Laboratory, which had produced the old 650 drum vacuum tube calculator, had their own versions of what to do, building on the 650 technology, and they worked hard to win the prize. When the dust settled, Endicott had won the prize with a lot of aggressiveness in terms of features and function that they promised in the 7070, moving more swiftly than the Poughkeepsie counterparts. Turned out, however, in horrible aftermath, the 7070 was such a complex machine from the Endicott designs that it did very poorly, fell far short of its forecast, and became more of a pariah than the success that we had hoped. But in the meantime, in Endicott, there had been a lot of work going on to replace those electric accounting machines with semiconductors. Still a lot of unit record equipment, punch card machines in around the world, and IBM had been struggling for 6 or 7 years to find a way to consolidate in an electronic machine the capabilities that were found in these assorted unit record machines of gang punches, collators, sorters, and calculators. And several tries had failed because the people working on the machines tried to build transistor machines around plug boards, the controls of those days of the electric accounting machines. And in hindsight, that's the reason that those designs failed. But a bright young engineer in the Endicott Laboratory named Fran Underwood conceived a von Neumann structure for a stored program machine that became the 1401. That was announced in 1957, shipped first in 1958, and it became, from our standpoint, the Model T Ford of the computer industry. Its selling price for a basic system was $2,495. Its rental was $2,495, unprecedented in contrast to the $20,000, $30,000, and $40,000 and $50,000 a month that people were paying for the bigger machines. We expected to sell just under 5,000 of those machines. Years later, when the dust had settled, we had sold something like 13,000 of those machines, and it paced IBM into the computing big time, bringing computing to a much broader set of customers. On the scientific side, the 7090 was a transistorized version of the 704, 709, just like the 7080 was a transistorized version of its vacuum tube predecessors. Something like 300 of those machines were sold. They were enormously profitable, enormously popular among the large scientific and aerospace fraternity. And that had something to do with some arguments that came up during 360's gestation that I'll tell you about. Switching to the 1620, there was a big gap in IBM's scientific line, a lot of clamor from the demanding sales forces for another line of small scientific computers. And a group in Poughkeepsie went to work, produced a machine called the 1620, but alas and alack, it wasn't a small binary computer. They produced a decimal computer for, I've always felt, somewhat loony reasons, but presence of the thing swept it in. Its rental, by the way, was $1,600, the first machine that we had that had less rental than its serial number, or its type number. And we sold a couple thousand of those machines to the then beginning to grow market that later decked, plowed, and cultivated and fertilized and grew so well. The 7030 was a special machine. Years earlier, Edward Teller had wanted a new super scientific machine for three-dimensional hydrodynamic calculations, and he had talked to IBM super salesman Cuthbert Hurd that I mentioned earlier. Cuthbert Hurd had dreamed over a beer or whatever that such a machine might take a couple of years to build, might take $2.5 million, and might run at 1 or 2 million instructions per second. Edward Teller went to Congress, got the money, and wanted that kind of a machine. And so a small group that John Griffith worked on, and Gene Amdahl, and a handful of bright people hacked away on a machine which we call LARC, Livermore Automatic Reaction Calculator. The UNIVAC team worked too on their LARC, and we had a whammy of a design, didn't we, John? It was a fine system. And we're just on the way out the door at the Poughkeepsie Laboratory to present our pitch to Dr. Teller, and Ralph Palmer, that genius, stopped us and said it's a mistake. The transistor technology was changing rapidly. We were going to build this thing in point contact transistors or surface barrier transistors, things in the early days that gave the best speed. And Palmer noticed the diffusion process had just been invented, promised better control of the speeds of semiconductors, and he thought it'd be a terrible mistake to build that fixed machine, waste 350 people, which was the estimate to build the machine. And so Palmer, to our disgust, several of us almost left the company, forced us to go out and tell Lou Nofri and Edward Teller that, put our proposal down, said, you read this, it shows the kind of machine we're capable of building, but we don't want to build that machine for you. We want to build something better, and we don't know what it will take, but we think it'll be another $1 million in another year. We don't know how fast it will run, but we'd like to shoot for 10 million instructions per second. Teller was furious. He brought the UNIVAC machine, the Lark, and we went back in to lick our wounds. And with the Lark machine commencing development and the able Sperry salesman selling it, a little panic set in 590 Madison, and the conclusion was we better, by jingo, fund the thing ourselves. So the thesis was that we would build a machine. It was internally called Stretch, for stretching the technology. It was that banal and that simple. And we set off to build Stretch machines. Later produced, I think 6 or 7 machines were produced. Its formal number was the 7030. Thesis was that it would be the fastest machine in the world. IBM lost its shirt on the thing, tens and tens of millions of dollars in terms of a business in itself. But several would tell you that lived close to it, as did I, that the technologies that flowed from Stretch and the architectures that flowed from Stretch had a profound influence later. All of us have a soft spot in the development community for taking on these one-of-a-kind, break the sound barrier kind of things for the attributes that usually flow. Be propitious to talk for a moment about organization in 1950. IBM was still a tiny company, although 1950 it was a few $100 million worth of revenue, a couple $100 million worth of revenue. But there was one vice president for engineering, and he handled all the business. He handled a little military business that we had, sold supplies, he ran typewriters, electric counting machines, the big hunk of the business, and the little tiny work that's going on in electronic computers. And so it was with manufacturing, and so it was with sales. That was a structure inappropriate for the growing size of IBM. As I said, crossed $1 billion in 1957. So the organization was changed. It actually started change in 1955. It took 4 years before the change was finally manifested, but in essence the change was from that particular structure to decentralization of new divisions. There was chairman of the board, Tom Watson, Jr. President was a fellow named Al Williams, who sadly died last year. Senior vice president for the World Trade Corporation, Tom's brother, Arthur Watson, Dick Watson. The World Trade's tiny business at that time, started years earlier, just beginning to grow, had their own marketing for the countries they served, their own service, had their own manufacturing. They had their own development and their own laboratories. And as engineers are, as you all know, they quickly rationalized that the Europeans needed something radically different than the Americans were producing. Sterling arithmetic in the United Kingdom and all those kinds of things, as Maurice Wilkes knows very well. And that crowd set out in the European labs to build their own sets of machines for their markets. World Trades in those days weren't big enough hunk of IBM to really cause the kind of fistfights that would go on these days, and so they were let go their course. I'd say in a summary that almost everything they attempted failed miserably, and because of the complexity and the uniqueness and the fact that the design was not rewarded with sufficient volumes to pay the way. But back in the mainstream, there was a senior vice president for data processing, now the core of the business. A fellow named T. Vincent Learson ran that. Giant Harvard guy, 6 foot, 4 or 5, awe-inspiring, tough guy. Marketing background. His organization was set up in a unique way, 3 divisions. The General Products Division in Endicott, New York, and in San Jose, California, with development and manufacturing. And their mission was very loosely called from free machines, we had no free machines, to $10,000 per month rental for a system. And in Poughkeepsie, New York, the Data Systems Division with development and manufacturing, and their mission was $10,000 per month rental for a system up to infinity. Most customers thought we were near infinity. Data Processing Division had sales and service headed by a fellow named Gilbert Jones, now retired, and in the heyday, probably the finest data processing marketing force that ever existed. One more important point. In this structure, the books resided with the product divisions. The marketing and service were run on apportionments that were doled out by the product divisions, which controlled the books. So the product divisions set prices, did the market forecasts, and had general responsibility for the financial health of the products that they produced. Let's look then, as we're nearing the point of what was to become 360, of how we stood. Here was General Products Division, $10,000 a month less for systems, Data Systems Division, $10,000 a month. And World Trade, little World Trade laboratories struggling to produce their unique requirements. And what I thought was, again, characteristic of Tom Watson, here we were in 1960 with 6 families of new machines. Most of them were doing well. The 7070 was not. The rest were doing quite well in terms of sales and profit, some far exceeding their forecast, like the 1401. The reorganization was just completed that I talked about in 1960, 1959. Tom called the new senior management together, and in what I thought was far-sighted vision said that these things are going to serve us well, but we ought to start thinking about where we're going, and we ought to have someone start working on where we're going. And so his conclusion was that the Data Systems Division should be given that mission, despite all the things that they were building, which was the 7070, 7090, 80, and the 7030, while the General Products Division worked on the smaller, higher volume machines. Now, one ironic note. In the reorganization of late 1950s, the General Products Division had machines up to 10,000. As I said, the Data Systems Division, the bigger machines. The Endicott Laboratory fell in the General Products Division, but they were the ones that had won the contest to produce the 7070, and they had stewardship over the 7070 in those days, and they were struggling with that machine, which was going through some troubled days. A bit late in schedule, sales weren't materializing, and a lot of trouble. But in the reorganization, as luck would have it, the Data Systems Division took over responsibility for the 7070, and so General Products Division had the privilege of transferring the 7070 to the Data Systems Division, who wanted that machine like they wanted tuberculosis. The Data Systems Division received the machine and all of its problems, and some of the leaders at that time thought the best thing they could do was get rid of it, and so they started a project in Poughkeepsie called the 8000 series to build a better machine than the 7070. And the leader of the systems gang in Poughkeepsie, a fellow named Stephen Dunwell, gave a simple charge to the engineers under him. I want a machine that's twice as fast at 7070 at half the cost. He had another little codicil on the thing. He wanted it packaged in one Rologon, which was one of the packages we used in those days in the bigger machines. So a little coterie of people in Poughkeepsie began hammering, sawing away on a new machine called the 8000 series. And bolstered by Tom Watson's assignment of a corporate mission to plan the next series of machines, felt they had the magic answer. And they proposed, in 1961, a new series called the 8000 series, built of contemporary technology. The 8106 was a machine that they had conceived to replace the 7070, and it was furthest along. Matter of fact, it was ready for announcement in March of 1961. To fulfill their worldwide mission, they quickly patched in other things around the 8106. They added a scientific bump to the machine called the 8108. Not a standalone machine. You had to buy an 8106 to perform as this thing shows in the scientific arena. Burroughs was working those days on a thing called push-down stacks and Polish notation, and that enamored a handful of people that were assigned the high end, and so they decided to build an anomalous machine called the 8112 at the high end. The General Products gang were so successful with the 1401 that they didn't want anything to do with the 8000 series in the Data Systems Division. The Data Systems Division needed small machines to handle peripheral management and to be the growth for their bigger machine, and therefore they needed a small commercial machine. And they hypothesized a thing called the 8103, a small business computer, and to fulfill the gap in the scientific area, they hypothesized a machine called the 8104, a scientific machine. These machines had some architectural similarities, but by and large they were quite dissimilar, and that was perhaps the fatal flaw, as were questions of the technology of the times. But the other factions in IBM were working away too. The General Products Division, with their success with the 1401, had planned taking the 1401 in all directions, down and up. I had a 1440, a 1410, a 7010 that ran right up into the kazoo of the Data Systems Division, 1401G. They had a 1620 Model 2. And because of the success of the parent machines, it was unlikely the Data Systems Division could ever, in political fights that would take place, get those machines choked off. So it looked like the General Products Division were heading for success with a competing line of machines to the new 8000 series that the Data Systems Division had. Little old World Trade Laboratories weren't alone. They didn't like the 1620. It was a decimal machine, and by George, the World Trade Markets wanted the small scientific machine. And so the Hursley, England laboratory had started the design of a 48-bit small binary machine called SCAMP-1. Very credible machine. It might have succeeded had it gone ahead. Unhappily, though, SCAMP-1 machine in the computer market for Europe in those days could not generate enough volumes to pay its way. And so SCAMP was in financial trouble of its own volition. The World Trade crowd, aggressive, then said, well, what the heck? We can build a faster version called SCAMP-2 on the base, get more volume, and fix the business case that way. And they strived to do so, proposing SCAMP-2, but it wasn't enough to fix the business case. And so, undaunted, despite the fact that it was a 48-bit binary base, parallel, they hypothesized a business version of SCAMP called SCAMP-3, and we're touting that around the company. So what was happening was the World Trades had their evolutionary plan. The Data Systems Division had the corporate mission in their plan that had some unsatisfactory parts of it. The General Products Division, based on the success of the 1620 and the 1401, had their plan, and the camps were all at war. Time was coming when a customer would call up and say, I'd like to hear about an IBM machine, and 3 salesmen get stuck in the door waving their wares, say, don't listen to him, listen to me. Now, there were more serious problem areas from our standpoint as we weighed the systems. My role in the thing came in January of 1961 when Learson asked me to leave Endicott, where I was working on the 1401 and the 1620 and the 1410 and all those wonderful little things, to go over to the arch rivals in Poughkeepsie. And Learson's instructions were simple. He said, look at that 8000 series. If it's right, build it. If it's not right, build what's right. And that's about the length of the discussion that I had with Learson in those days. We operated in a different way in those days. Now we're bureaucratic and go through a lot of procedures, but the fellow I was to report to wasn't even told that I was coming before I got there. One of the problems that we had is that peripherals of those days had to be customized by family. If you wanted to build a peripheral that was optimized for parallel binary machines, that was tough. If you're going to build something that was serial by character for the commercial machines, that was something else. None of these machines had enough volume to sustain new investment in peripherals. And so what happened was that the peripheral groups in San Jose and Poughkeepsie tapes, San Jose disk files, hacked away building whatever they wanted to build, and then we adapted those devices to the processors with adapters. And here's but one file that went across a number of machines, and there were 7 or 8 or 9 different kinds of adapters that put those disk files on those machines. And in those days, the peripherals were way out of speed with the processors. It was possible to go from one processor to another and get 100% gain in internal performance, but because of the inadequate peripherals, to get 10 or 15% gain in performance, if that, and that's before you take into account the programming. Second thing is that the circuit technology was different by type of machine. Here I must say that Ralph Palmer and senior management of the business had strived hard to standardize on transistors as they swept in. It used to be in IBM that every project had their own designer, and he would hack away designing the circuits for that project. And the projects loved to have that, for they felt they were optimizing their product for whatever the market they were heading for. But Palmer, with transistors, had forced the establishment of central circuit design laboratories, with these central laboratories providing circuits to the various groups. A big fight in the business in those days, but in hindsight, a right decision by any measure. But trying to standardize, we'd set a printed circuit card thing called the standard modular system, about the size of your hand, held one circuit of discrete transistors, resistors, and diodes and capacitors, and a lot of automation equipment to insert these components, to solder them in place and test them and all that sort of stuff. But in the early days of transistors in the standard modular system, the theory was that if we really did it right, about 100 of these card types would serve all the IBM machines. And wouldn't that be ducky for service and service training and engineering refinement and all those kinds of things? But by 1960, the thing had exploded out of control, and there were more than 2,500 card types. The standard modular system and all that plan had gone afoul. There were so many card types, the engineering force had time just fixing those that didn't work, let alone improving those that did. And of course, field stocking and field engineer training and all those things were expensive and complex. Perhaps the worst problem of all was programming. In 1960, in the very heyday of the 1600, 7000, 1400 series, the programming budget in IBM development was $5 million. And that was less than 5% of the development budget in those years, in the heyday for those types. Those in the room know that the kind of thing that happens under these circumstances is that not only do you have to produce a Fortran for each type of machine, but there had to be a Fortran for the disk version of the 7090 and the tape version of the 7090, and assemblers and utilities and sorts and all that kind of thing. It's really a three-dimensional sort of thing. So we were in a big mess with respect to programming in 1960, and we knew it. We had split our customers' houses with scientific and business. Boeing is a great example I love to quote. Two very able fellows with their shops, one had 7080s, one had 7090s, vying for funds, vying for applications, vying for people. But what really was happening behind the scenes, in our view, was the business folks needed more and more of the logical and computing abilities of the scientific side, and the scientific side needed more and more the variable field length and alphanumeric capabilities of the business side. But for our customers, we put them in two camps, and the camps were competing. The user's programming investment was high, it was growing rapidly, and the customers sent us a signal with the 7070. No matter how exotic the architecture, no matter how much better the price performance was in contrast to older systems, they weren't going to make the move. And lastly, that most of them couldn't afford to convert and didn't, and therefore we spun a lot of systems. What is a summary of the whole thing is in this fairly accurate picture of 1960 IBM development resources. Most everything went into the evolution and propagation of processors. Tiny amount went into peripheral enhancement, mostly tapes, a bit going into disks and printers, and a tiny amount, I said, $5 million in 1960 for programming systems. What was hypothesized by a coterie of a new team that came together in Poughkeepsie. What happened was we went to look at the 8000 series in early 1960 and concluded the 8000 series had lots of frailties. Incompatibilities between the architectures themselves were a major frailty. Other missing elements in the program in an old technology. And so what took place in the May, June, July period of 1961 was a conclusion to try to build a new family of machines. And there were several foundations of this hypothesis. The first was that each machine would be equally adept at business and scientific calculations. The second was that while it was easy to produce machines that were upward compatible, the small one has 10 instructions in its repertoire, the next one's got 20, including the first 10 and all that stuff. We're going to strive to make those machines upward and downward compatible. So if a machine had the required peripherals and had the amount of core that was specified by the programming, whether it's a big machine or a small machine, could run the programs. But more important, it unfettered the programming from the specific machines themselves. Small entry-level programming could run on the whole family. Giant programming, the more complex programming with higher function, could run on the whole family. And to fix the I/O problem, the thesis was standard interfaces. Let's standardize on all the interfaces for peripherals, and let's have the peripheral people adapt to these standard interfaces so that our programming won't be reflected or won't be wrecked by new peripherals, and new peripherals can slide into these high volumes. Lastly, the thesis was to build the machines in a new technology that was going on in IBM. Internally, it was called the compact technology. Basically, it was a miniaturized hybrid, micro-miniaturized hybrid technology. Instead of that palm-sized card that held a circuit, fingernail-sized chip held a single circuit. A fellow named Eric Bloch, a fellow named John Gibson, and I agonized a lot in 1961 about whether we should go to large-scale integration. A lot of writings in those days by science. Some worked in large-scale integration. The theory was that maybe we better do that as opposed to build this radical new series in this hybrid micro-miniaturized technology. But fortunately, we elected to build what we had in hand. Heavy investment went into automating the production of this technology, and it was very sophisticated, and in time, enormous volumes were turned out at high quality and very low cost. The architectural structure of the machines had a base structure of being decimal, had binary options, having variable field length characteristics, and having optional floating point, so it could be adept each machine, scientific as well as business calculations, and hopefully we'd put in the machines the basics to allow us to expand into new applications as they unfolded. There's another problem, though. IBM has an aggressive sales force, and we feed them on commissions. They get a stipend that lets them eat bologna sandwiches, but if they want to eat steak, they got to sell. They've got long-range viewpoint that says tomorrow is too long. And they have a tough time waiting for a few months, let alone a few years. Anything as significant as shifting the gears to this new technology, these new architectures, this new programming, was going to take a bunch of time. We estimated we'd announce in 1964. Turns out we did. We'd ship in 1965, but this is 1961. And to the sales force, it was an eternity. In the meantime, Seymour Cray and CDC and lots of good folk were beginning to succeed with competitors for the IBM product line. And the sales force felt that their homes were burning down, and they wanted some answers quick. And so we put in place simultaneously some programs to do what I hate the word, but we called them then and I call them now temporizers. This was the product line that I described before of what IBM had, the really 6 different product lines that IBM had, with many versions of each of these machines in the product lines back in that period. And the temporizers that were put in place were to build a higher speed version of 7090 called the 7090-41. It was so successful that we built a 7090-42 and actually worked on the 7090-43. A couple more versions were built of the 7070 called the 7072 and the 7074, hopefully to jack up its lagging sales. They didn't. Bigger version of the 1410 was built for growth for the 1401 customers, the 7010. The 1620 Model 2 was built, and in that big gap in the small scientific area, machines related to the 7090 architecture called the 7040 and 7044 were built. All these machines undertaken starting in mid-61 and some announced in 62, all announced by May of 1963, while the sales force had the stresses, did hold the line. IBM suffered some losses, but were able to keep the sales force literally at bay during the time the gears were being shifted to System 360. What System 360 did in terms of the problems was that, I've already said, the peripherals by the standard interfaces were standardized across all of System 360. The circuit technology was the new solid logic technology that was standardized across the machines. The programming was independent of the hardware. The scientific and business split was solved by integrating into one machine the capability to solve all those kinds of problems. And the key issue was programmer conversion. For a long time, Fred Brooks and Gene Amdahl and those people, John Griffith, worked on how to do this. The first thought was we'd have machine translation. And some very bright people worked on thesis that just dump your machine and your program in this hopper and we'll crank it out. It'll be fit to run perfectly on the new architecture of System 360. And a couple of years of hard work and several $1 million of investment concluded that that wasn't going to make it. Theory then was that maybe we better back off to machine-assisted translation, where we would translate as much as we could and signal the things that had to be handled manually. At the time that was assessed, it turned out that you had to do most things manually anyway, so that was discarded. There was look at simulation, but simulation was too slow, an order of magnitude, 2 orders of magnitude too slow, and we were in a dilemma, for we knew that this series was so different. The 707 had painted the story the customers weren't going to convert. We had to have a tool. Necessity breeds invention, and a couple of fellows in the Endicott laboratory found the solution. They found that if you look at a 1401's registers and data flow and looked at that in the light of a 360, the 360 had all the same registers and more, and all the same data paths and more. And since we had decided to use some of Professor Wilkes' work in the controls of these machines, namely read-only memory instead of hardwired logic, the controls were vastly simplified, and so it was no big deal to add to a 360 machine the instructions for a 1401 and literally throw a switch so that the machine would take the shape of the 1401 and run credibly as a 1401. And so it proved out with the 7070, the 7090, the 7080, the whole schmear, fortunately for IBM. And they ran not at full 360 performance, of course. They ran not without some problems and some programming that had to be done to help these things happen. But by and large, through the combination of read-only memories for control, which let us add the instruction repertoires of the older machines, and the things we did in the control of the machines, so the 360 machines would take on the form of the older machines. The customers could run the old machines at their leisure, at reasonable price performance, and then convert at their leisure to the newer stuff when they wanted to. I'll tell you, some people are still running in emulation mode all these days. Now, we got down to the wire. 1962 was the period of, can we make it? Can we design it? And for a while it appeared that we couldn't design a machine who was small, at least small enough cost at the low end, but had all the instructions of the big machine, and a machine at the high end that was limited by the features and function we wanted to put into it so it could stay compatible, upward and downward compatible, and yet perform credibly. Fred Brooks finally set up a group of design competition teams. 13 of those teams were put together, and the design competition brought in the solution. And finally, in the third quarter of 1962, we concluded we could build a machine, a family of machines that was upward and downward compatible, meet the cost goals, etc. That was done. 1963 was the year of building the temporizers with the other teams that were doing that, but the mainstream team was hacking away on 360. We call it the new product line in those days, and it was hard work, long hours, but it was wonderful work because the team felt they were doing something very significant. Then we got down to the last weeks before announcement. We were looking at announcement in maybe January of 1964. The plan was March of 1964, but some pressures to do it earlier. And the eminence of that announcement brought a lot of people out of the closet to argue about whether 360 ought to be done. The opposition was curious to me, not surprisingly, was the finance community. Finance community stayed properly conservative, said, you got 6 different families. If the competition wipes you out in one of those families, it's only 1/6 of the whole schmear. You don't lose the corporation. So why do this thing that puts all the eggs in one basket? It's a tantalizing question. I was always curious of the corporate strategic planning, the big boss that ought to be looking at the future, thought that all the eggs in the basket thing was too much and that ought not to be done, and rather we ought to propagate the series that we had invested in, the 6 different families in years past. Fortunately, those folks didn't last long, the corporate strategic planners. A couple of them went to another couple of companies that have since gone under, proving a viewpoint that they weren't all that smart. The engineering community and my friend John Griffith remember very well what happened. They didn't like the word length or the addressing of the 360 family. We'd chosen for 360 to have 32-bit words, double precision with 64-bit words. The wonderful 7090 was a 36-bit machine, double precision with 72 bits. You don't have to be very deep in math to know that 36 bits doesn't map very well into 32. And the community were in arms, outraged over that. Secondly, the community liked direct addressing. All of our previous machines that had direct addressing, and every machine we built was out of memory before we got the first machine into production. And so we'd gone to a scheme called base register offset to be able to address millions and millions of characters in the machines. And the scientific community didn't like that, the scientific programmers and the scientific architects and the proponents of the 7090. And they went increasingly frantically to the senior management of the business to complain that this machine was a loser. The architecture was a dog. And the senior management was in a lot of dilemma at that time as to what was right. And we had many long hours and long nights to debate these fundamental issues. The whole thing came to its Armageddon really starting December 5th, 1963. Honeywell announced a thing called the Honeywell 200. Some of you might even remember it. Honeywell 200 was a 1401 machine, only it ran 4 times faster than the 1401. They had a wonderful program they called Liberator, which would let you run your application programs through Honeywell's Liberator, and if there were machine-dependent things that took place in your programming, Liberator would either flag those or automatically translate those so they'd run on the Honeywell 200 machine. It's the first time that anybody had brought out a machine that was identical to IBM's machines, and part of the company panicked over this. The General Products Division, which had stewardship over the 1401 and that family, really were troubled because that was the mainstream revenue and profits of the IBM company. And in their panic, they decided that they would postpone building the new product line and proposed instead in January 1964 to the management of IBM that they build a 1401 Super. It's going to be 5 times the 1401. And for a while it looked like the 1401 Super was going to go. And some of us lived in near state of heart attack as the debates went on. But suddenly somebody realized that if we produced a 5 times 1401 and Honeywell produced a 4 times 1401, the whole question would quickly reduce to plant capacity. They'd sell 5,000, we'd sell 5,000, there'd be a gas war. But worse, the 1401, invented years earlier, was wholly inadequate for the applications that we saw, whereas there were so many attributes of the new product line family that in February, in short order, the smoke-filled room decided that while there were flaws and warts on her, that we had to go ahead with the new product line. They wanted to announce it in March of 1964, and when we decided when we could do that, that turned out that the only time was Easter. Somebody thought that would be appropriate since it was almost an immaculate conception, but we didn't do that. We deferred and announced it on April 7th, 1964. See where it went, and then tell you some of the successes that accrued and some problems that accrued. First place here, we are now on an $8 billion scale, and these are the things that you saw before up through 1959. Here's really the output of System 360, which by 1967 was the dominant part of IBM's revenues and profits. And here are the profits of 360. You see a little stress on the margin during the years of investment then a return to levels that are still very prideful today. 13%, Gordon and some in the room will tell you, are terrific if you can maintain those. More important from the standpoint of where we were and where we were going, we substantially diminished the investment in processors. The evolution of processors with new technologies that were constantly flowing put substantially more into peripherals and put substantially more into programming. Now, at the time, April 7th, 1964, we announced really 5 machines. The Model 30 was produced in Endicott. Model 40 was produced in Hursley, England. As a side point, as part of the decision to join the team, the World Trades wanted to play a role in the 360 development. They were a young lab, full of bright people, but I wanted to give them some bits and pieces. But Van Leersen said, absolutely not. They have to have a head-held high role. We want to give them a whole machine. So we did. We imported a lot of U.S. people over to help them. But today, and shortly after that, they became one of the senior labs in IBM's development community. Poughkeepsie produced the 50. The 60 and the 62 just had differences in memory in the higher performance Model 70. Later, through the last part of the 60s, there were successors or additions announced. The low-entry 360 20 and 22, the 25, a scientific optimization, Model 44. Some new memories came in to the 65, which replaced the 60 and the 62, and the 75 with those new memories replaced the 70. The Model 67 grew out of MIT, and MIT's criticism of System 360, and I'll take a moment to tell you that story. That Watson had told me in the early days that MIT were paragons of computer direction, and he wanted to make darn certain that we stayed close to MIT's thinking. And during this period, busy as we were, I would come occasionally to MIT and talk to some of the people. And I'd send people up like Gene Amdahl and Fred Brooks and others to have their discussions with MIT. But in retrospect, they didn't hear us and we didn't hear them. And we didn't speak clearly enough to them. The thing was announced on April 7th, and we all settled down to the wonderful task of making it happen. And finally, on June 6th, 1964, I had a moment and came up here on a Saturday with John Koch, the architect I mentioned earlier, to visit Corby and Fano and the people at MIT and to hear some other speeches at the B School that Saturday. And I went over to see what they thought of 360. I'd been out the street a couple months. Corby and Fano told me that they didn't like it. They had some reasons. 3 of the 4 reasons were trivial and could have been fixed quickly. One was deep in the concrete. That was MIT's view that time sharing was just around the corner, and that dynamic address translation was a fundamental part of any machine's architecture of the future, and without it, that management of storage by the programmers would be an impossibility. Still some debates, not many these days, as whether MIT was right, but I decided that day they were right and we had missed it. It took us several years to fix it, but we fixed it later on and got the line into dynamic address translation. But at that moment, we produced a special version of the 65 called the Model 67. It was built for a coterie of leading-edge customers like Bell Labs that wanted time sharing in their machines and demanded dynamic address translation. And happily for us, MIT decided to buy a General Electric machine, and not the 67 that we were frantically putting together to answer their specifics. But at this time, through the late 1960s, the only machine that had dynamic address translation was the Model 67. Incidentally, a special version of that was produced called the 9020 that became the machines used in the FAA's en route traffic control system. Now, we thought in those days that we'd be lucky if the thing would last one generation, 3 or 4 or 5 years. And if we were really lucky, it would last 8 or 10 years, a couple generations. But as Bill said in his introduction, the thing has lasted 20 years, and we're working on stuff now for the 90s, right or wrong. Maybe it won't make it, but the durability of that architecture has far surpassed our expectations and our dreams. In the late 1960s, technology had marched on to the point, instead of 1 circuit per little solid logic chip, we could do 3 or 4 circuits per chip. The early days of large-scale integration. And so we produced a family of machines, the 138, the 148, the 158, and the 168. And there's some detail in between of earlier what were called vanilla machines that I'll skip. Bottom line is that all these machines had dynamic address translation, and our programming was substantially modified to accommodate dynamic address translation. In the late 70s, higher performance machines, the 303X machines, came out, all direct members of the 360 family. And today, well, 1979 and thereafter, the 43XX machines, the 3081s, the whole variety of machines, but again, members of that family that added up account for more than 100 billion of revenue in handsome profits indeed. In terms of how the business did, here are the charts you've seen before, only now it's a $30 billion scale. And this takes it through 1969. Here's the decade of the 70s. Now it's getting obscene, I admit, $26.2 billion. But strong compound growth. And margin has stayed strong even through the thick and thin of the recessions of 1971 and 1975. I'm going to just go on for just a few more minutes to tell you a couple of epilogues on the 360 thing. I said earlier that we tried to design into the roots of the machine the things that would let it work in new applications of the future. One that we smelled clearly in 1961, 62, and 63 was teleprocessing, for it was beginning to come around the corner, but we couldn't get our hands around it enough to know just what to do. And so we sort of put the hooks into System 360 to add teleprocessing capabilities when it came along as best we could. Here was our expectations at the time we announced System 360 in April 1964. This is just the Models 40 and bigger, the little old Model 30, the high volume unit. Half the volume of all the series was viewed to not really be in the communications environment. The estimate was that in the United States we'd sell 2,500 of the 40, 50, 60, and 70 machines, and a third of those by 1970 would have remote terminals and thus require communications facilities, hardware, and programming. What actually happened was, fortunately for old IBM, that we sold twice as many of those machines as we had expected by 1970, never mind the series yet to come. And by 1968, we had already passed what we'd expected to not reach until the end of 1970. And by 1970, that 2.5 times what we'd expected in terms of teleprocessing. It turns out we were so consumed with just building those machines and the complexities of the programming that we really didn't tend swiftly enough to communications. So a lot of lash-up things happened to communications during this time. I'll not explain the alphabet soup except to say that one little laboratory or this customer or that would produce something, and it was a nightmare for communicating in those days. To make a long story short, starting in about 1969, early 70, we set out to do the same thing to the communication subsystem that we had done to the central processing subsystem. It's a thing called Systems Network Architecture, and some of you may be familiar with it. We immediately offered it up, and it's been generally accepted as an international standards organization architecture, which straightens out the protocols, disciplines, structure of the communications subsystem. I'll just say that back in 1973, when we were finishing work on SNA, our hope was that worldwide that we might install early in the 80s 3,500 SNA systems. And last year, the team gathered to have a nice dinner and a little music to celebrate 10,000 customers. These days, in the heyday of the PCs and all that exploding workstation, that we're now talking in terms of hundreds and hundreds of thousands. SNA has had, I'll not go through them, of course, but there's been a succession of sophisticated additions to the structure, the sorts of things that you might expect once the base is in place, taking care of alternate routing and automatic line outages and dynamic reconfiguration and non-IBM terminal attachment and all those kinds of things. Now today there's an explosion, as many of you in the room know well, especially Gordon, in computer and communications. Can't tell them apart. You find computers connected to computers by communication lines, often tens of computers talking to computers, and they have control units connected by communication lines with hundreds, often thousands of terminals. And then, of course, there are many computers pioneered by Gordon and the marvelous DEC company. Whether it's real-time applications or batch applications or interactive applications, they too have distant communications from terminals. And more, these terminals on minis need access to central databases and vice versa, so there's an explosion in communication. So if I would characterize where we are today and the way we're spending our resources, or rather the end of the decade of the 1980s and about the same today, you see that we're spending a good deal more on communications. Programming has come down, although it's a handsome bill. Input-output peripherals continue up. You see an upturn in processors. I'm not going to wash much linen except to say that we didn't learn our management lesson well. The 360 did very well, but in the smoke-filled aftermath, and everybody was laying around breathing hard about what happened, there was a conclusion that we risked too much. We did risk the whole damn company, and it wasn't right for the shareholders to do that, and that we ought not to do that kind of thing. While we wanted a thing like the 360, 370 line as far ahead as we can see, we ought to have other systems too. So through the decade of the 1970s, a variety of other systems began to appear at the mid-range, a thing called the 8100, Series 1, System 32, System 34, System 38, and whatnot. And we're right back in the old mousetrap we were before. While these systems are fine in their own rights, the support of the evolution of these systems is untenable, and worse, when customers want to connect them, those weren't properly allowed, and so they're not doing as well in the marketplace as we hope. So we're back again, spending more on processors and working hard on how to converge our systems sometime in the future. Just to have a couple more charts. Communications explosion and the great rewards that came from teleprocessing and indeed the 360 base caused us to decide that we ought to do something significant in communications. We worried a lot about AT&T, who were making serious noises about coming in the computer game, and we worried that, like I'm sure Gordon and his comrades at DEC in those days worried, that if AT&T came in and controlled the communications, and there was so much of the business in communications, there might really be tough competition. We ought to find an alternative. Something that attracted us was communication satellites, and we've invested in communication satellites, own a third of a small company that's providing those services. And it's a double-edged sword. It's pretty good business in its own right, and secondly, it's breeding new communication capabilities for teleprocessing users and keeping the competitive pressure on the telephone companies, and we think that's good for the industry. If I would summarize in my last couple of charts, I guess I have 3 left, how did it all happen? I'm not trying to blow the IBM horn. First is there was a strategically minded management. The very heyday of the systems, predecessor systems in the 1960s, Tom Watson Jr. set a team out physically to work on the next generation. A broad direction was set, but the senior management delegated the detail. They didn't strive to manage the architecture. They heard the fights, and they tried to resolve the fights and understand the fights, but they never stepped in to say that we're going to go to 36-bit words, or we're going to do this, or we're going to do that. The demands on the organization stressed IBM to the limits, and IBM has been organized and reorganized again and again because of what happened from System 360, but we've lived through those times. Lastly, I'd say that through a lot of criticism that senior management, old Tom and Al Williams and those folks had a lot of tenacity and did take a lot of risk of the corporation. I'd say, was it worth it? I'll just say that from the period 1964 to 1980, the actual profits after tax in those machines was far, far greater than the total sales that we'd anticipated back in 1964. So in the sense of what we're in business for, of earning money, it was an outstanding success. But I would say more important, it gave us a foundation to move new resources into new peripherals, to do the things like SNA and all that went with it in terminals and teleprocessing, to do some specialization things in certain industry areas, and to diversify into things like satellites and other things as well. It's given us a great new flexibility. These things don't come without their problems, and for those that are really getting fidgety, this is the last slide. It brought something that scholars will say might have been too much of a pain. That in the 1960s we saw the first of peripheral competition. People were locked into our tapes. They didn't like that. A little company in Oklahoma called Telex started making copies of IBM's magnetic tapes. And a lot of customers trooped off to buy those just to signal to us that they didn't want to be locked into IBM. Shortly after that, manufacturers producing copies of our disks and then multiplexers and then main memory. In the 1970s, we saw all kinds of terminals and finally the piece de resistance central processors. Fujitsu, Amdahl, Hitachi, Magnuson, all those kind of folks, and programming that competed directly with IBM's 360, 370 product lines. That was expected. We knew that from the time we started to conceive this series, and our rationalization then was that that's not a problem. This thing will come, and all we have to do is ensure that we're best, that we have the best technology, the best systems, and that kind of stuff. Those catchwords sold because we believed it, and we intended to do so. But the negative that came out of the thing that was not foreseen was antitrust legislation that darn near brought us down. In the last days of Lyndon Johnson's administration, as you know, the lawsuit was filed by the Department of Justice. Telex filed a lawsuit saying we had infringed on them, damaged them with our predatory practices. The thing went to, we filed against them for stealing. In a curious decision in 1972, in a district court in Tulsa, a judge found for both of us, found Telex guilty of stealing and fined them $21 million, found us guilty of harming Telex, fined us $120 million, and after trebling under U.S. antitrust law, it went to $360 million. IBM stock, end of 72, went from $365 to $140 in a hurry, and immediately a lot of other folks thought they'd been wounded too, and filed lawsuits, Transamerica and Memorex and Calcomp and Marshall and Foro Precision and all those folks. And so for a long time, with zillions of dollars and senior management time tied up, that we went through the gauntlet of the antitrust trials. That story's over for now. I hope forever. I'll say for now, in the sense that all these cases gone to court. We've won every one on the merits. And just a week ago, the last one, the Transamerica case, went to the Supreme Court. The Supreme Court refused to hear it, thus upholding the appellate court's decision. And a little over a year ago, the government dropped their long suit as without merit. So that enormous barnacle is scraped off of our side, and we're back to getting on with life. Yet, the argument goes on that had we not standardized and done all that stuff that became System 360, we wouldn't have had these kind of copies, and we wouldn't have had those lawsuits, and wouldn't have had that pain, and was it all worth it? Of course, ladies and gentlemen, I have a bias saying that the driver of this whole thing is the end user, and we have an accountability to that user. We have an accountability to conduct ourselves in a fair way, and I think that the decision was the right decision. I can't tell you that if IBM were faced that decision today, bureaucracy that we are could make that decision again. I can't tell you they couldn't either, although I'm sure it'd be much tougher these days. But the bottom line is the thing was conceived, born of need, weathered a lot of tough gauntlets, went on to be a success, and to be a significant part of the computer industry at this time. Thank you very much.
We have time for a few questions if anyone would like to ask them.
What effect, if any, did IBM's experience building machines like the ASCC and SSCC have on moving them into the electronic computer business?
Well, I think all the steps. Is that still on? Yeah, I'll just hold it. In the steps of the days like the MARC machine at Harvard and the selective sequence electronic calculator, and all those machines were a step forward in refining IBM's understanding of the possibilities for very large computing engines. But I have to say that until the early 50s, 53, 54, there wasn't much appreciation that there really was a market, and that was the direction that IBM should turn. But they all drove a stake in the ground in terms of our understanding. Yes?
Just why did you pick 32 bits rather than 36?
Well, it was, we were looking at the homogeneity of the architecture, and I'd have to tell you that while it probably was not a bright decision at the time, we thought that an exponential power of 2 would simplify the overall structure of the machine. Since 32 is a power of 2, we were looking for simplicity in the machines. I would say in hindsight that we could have made it 36 or 40 without untenable consequences, and the machines might have been better for it. Yes? Oh, yes?
I lived through a nightmare called FS and never really understood it, but I think that's something you do with it. Explain it at all?
The question was, we had another nightmare called FS, and could I explain it? About 1970, we were on the verge of announcing System 370, the technology upgrade of System 360. And at that time, in the smoke-filled room in IBM, there was a viewpoint that 360 was probably running out of gas, and there were more things that we should do architecturally. And so a small group was chartered to look at a wholly different structure called FS. And the recession hit in 1971. It wasn't viewed to be terribly long, but it lasted a year and a half, almost 2 years, and brought a lot of pressures that later we rationalized as one of the reasons that 360 didn't look so strong in 1970. Nonetheless, the FS program struggled along, trying to do some really bold things in technology as well as architecture. The technology thing that we were trying to do was wafer scale integration, that you now hear about from Trilogy, the thesis of instead of carving up the wafer into chips and testing them and throwing the bad chips out, that you keep the wafer intact and interconnect on the wafer. It turns out that the deeper we got into this theory of very big memories in the FS series, that we couldn't get the quality, the yields that we needed. The whole thesis of the big chips fell apart. And secondly, the deeper that we got into the design of FS, the tougher the migration and conversion problems loomed. And thirdly, that dynamic address translation had gone through its startup period, had hit the marketplace. It showed there was substantial new life in System 370, and all those forces combined to say the proper route for us was to continue propagating System 360 architecture and not throw it away. Question in the back.
What happened to first you had the 1620, and then the 1130, and the 1130 custom had after that pretty much migrated to the mini computer copies.
I should have put the 1130 on. It was just an oversight on those charts. It was another machine that, as was another machine called the 1800 that came out. None of those machines ever achieved substantial volume, but the theory that went on in IBM at the time was that a handful of those special machines were required by the scientific fraternity. While some of my colleagues and I argued that 360 architecture was perfectly optimizable for scientific applications. So the Model 44 went into combat with the machines that you're talking about, and both were done and neither did well. Failed their forecast, and the conclusion was that the market requirement was not so significant. Then along came Ken Olson and Gordon Bell and a lot of bright people that showed it was, and we'd missed it. And so I'd have to stand here tonight and say that faced with an opportunity to move into mini computers at the very beginning, as did Gordon and Ken and those people, that we decided it wasn't that big a deal for us. Then belatedly, with Series 1 years later, tried to get back in the game. Yes?
I was happy with the Series 1 that it wasn't 360 compatible when it came out. I wondered
Why?
why not?
Series 1 wasn't 360 compatible because that meeting had been held in the smoke-filled room that said we'd risked too much, and now maybe we ought to start specializing in building some machines. And a little crowd of architects anxious to do their thing came out with Series 1. I think if you told the truth that while Series 1's done pretty well, you'd say it's a pretty ragtag architecture.
Well, but I wondered why it wasn't a 360. I mean, was it risking the revenue base of the
Oh, no, not at all. There were arguments that the 360 structure could have produced what was the Series 1, and I believe devotedly that it could. Rather, the conclusion was we'd put too many eggs in the basket. Successful as it was assured to be, the theory in the early 70s was that maybe we ought to build some things that are different. That was a dumb decision, in my opinion, something we're going to have to fix. That isn't to say that everything is going to be 360, 370 compatible in the future, but I think you'll see a lot more convergence from us in time. Yes?
Why was it such a difficult decision to decide to emulate all your previous machines? You sounded like...
Well, it wasn't a difficult decision. What had happened was we didn't know about emulation at that time. And what had happened is Professor Wilkes and his group had worked on read-only memory. Our English laboratory had picked up the theory, had built a tiny thing called an E.T. Biller to prove the theory of read-only memory. And we had made a propitious decision, quite independent of emulation, to put the controls in all the machines save the biggest, the 75. Using read-only memory. And we struggled with other alternatives for conversion, program translation and machine-assisted translation, simulation, and those good things. Backed against the wall with a machine that was about to be born with radically different architecture and no clear migration path for our customers, that emulation came sort of in the middle of the night as the fact that we could actually structure our machines like the old machines, and those old programs could run unchanged. It turned out to be kind of a miraculous solution. Yes?
You spoke of some compatibilities and standards. You mentioned one that's, it seems IBM resisted. That's ASCII. Do you have any comments on why that went on?
Well, yes, there were debates in 1963 as to whether the 360 ought to go only ASCII and be the ASCII entrant. And I'll simply have to say that as we viewed the customers and their needs, that our conclusion was that that was a wrong decision, and therefore, by default, we didn't support ASCII at a time when several, including many inside the business, thought that we should. It was a thoughtful decision. It was a hard decision.
I'd like to intercede here, hold off the questions. You can join us all in the other building for wine and cheese, but I'm going to use my prerogative to ask you one last question. If you could give us some insight on the 370 version of the PC that's just been announced. What was the origin of that?
Well, the VLSI has brought us such capabilities, and with the, I'd say, unexpected success of our PC, that it didn't take long to realize that on the PC base that we could build 360 compatibility and thus provide a 370 programmer's workbench. So we started working on it, and it came out fairly quickly. So it was nothing magic, made possible really by the giant strides of the technology that we have in hand today.
Thank you very much.